Okay, this is chapter 15.3, buffering capacity. The definition of buffering capacity is the amount of acid or base that is neutralized by the buffer before a significant transformation in pH value, whether it drops significantly or raises. In other words, it is the ability of a solution that the solution has to resist changes in its pH. The buffer capacity varies based on the concentration of the acid and the conjugate base of the buffer being used. When the concentration is greater, of course, the capacity will be greater. This also means that if the concentrations are lower, the lower buffer capacity will measure. Okay, pH range is also associated with buffer capacity because it measures the pH range where the buffer is effective. A significant change in the pH is a change of 1 unit. So when there's a shift in pH by 1 unit up or down, you can see that the buffer capacity is there. One example we were given, a pH change from 7.6 to 8.6 is a significant change in the pH. The buffering capacity in this case shows the quantity of the base that was required to drop the pH by a factor of 1. Even though the pH increases, it still gets more basic. This is an example of how buffer capacity is associated with the pH range. To calculate the buffer, 2 different types of calculations can be used. Stoichiometry calculation and the equilibrium calculation. In the first type of calculation, there's 4 general steps to simplify it. The first step, you'll balance the given equation. The second step, you'll convert the given unit, if not already moles, to moles. Step 3 is using the mole ratio. You'll find the moles of the substance that is yielded by the reaction. And step 4, you'll convert moles to the desired unit if necessary. It may be moles, but if it's not moles, you have to convert it. Okay, so we'll work with this example. We're going to determine what volume of H2 is needed to produce 224 liters of NH3. Okay, step 1, we're going to balance it. So you see, this was our original reaction. We added a 3 in front of the H2 and a 2 in front of our final product to balance it. Next step, we're going to convert the given unit to moles. In this case, it's converted from liters to moles. So this is our conversion factor. We set it up and we realize we have 10 moles of NH3. Step 3, as discussed earlier, we will use the mole ratio. So we set it up. It's going to be over 2 moles, and that's going to give you 15 moles of of H2. Step 4, convert moles to the desired unit if necessary. In this case, we are converting it back to liters because the question asked for liters. So we have our liter conversion here again, and it's going to equal to 336 liters of H2. And this is our problem again. Determine what the volume of H2 is needed to produce that many liters of NH3. And we found our answer is 336 liters of H2. Okay, and then the second type of calculation, the equilibrium calculation, can be performed when using the following equation. So basically, you'll just plug everything in, and that's another way to find the buffer. And that's chapter 15.3, buffering capacity.